Okay. We believe we're back online. So, please make sure to refer to check the references for the reading and video material, which is plenty of hours of work in watching videos and casually looking at the references. And I need to compile some more references and send that out. And if there is any interest by participants in questions or having a final wrap-up discussion, please contact me. I'm available for at least these 4 hours. I'm glad to entertain questions or discussion, and to facilitate that, you can contact me at my email, Damon Bell, USFQ at gmail.com. Also, I just playing a little bit, I set up a what do you call it, group at LinkedIn. This is a new group. I set it up about 10 minutes ago, just to allow folks to, first of all, connect if you'd like to make connections if you use linkedin.com. So this is www.linkedin.com. If you don't have an account, you might want to avoid this or start an account. But there's a group. It's called, what is it called? In just a minute. USFQ QSAR intro statistics. This is the name of a group at linkedin.com which I created, and if I did it correctly, it is wide open to that you could post comments or use it to get in touch with other folks in the seminar if you'd like. It would be great to get a list of people together and maintain some kind of contact, or I'm willing to entertain further discussion if folks would like to do that. And you can post comments, I guess. I will try and look at this sometime. Then I'll need to email later, Belen. We can do evaluation by email, right?
Yeah.
Okay. So we will plan to do an evaluation by email. So this would be something quite simple to evaluate the fact that people respond to the email, respond to the evaluation, so do it. If it is possible that the evaluation is not executed, but our current thinking is to have an evaluation, right? This is like a final exam. For the seminar. And so the plan is that we will email something, email, and then participants for credit fill form which will ask some very basic questions to see if you were alive at the time when you heard about statistics. I have in mind, things like, so some very brief review is
I think you should start with the class, and then I'm gonna email them and explain.
okay, great. All right. So we will go ahead and start on our last day topics. I'm going to go a little bit free form here and see how it goes with trying to survey, provide some description of alternate methodologies and review. Let's see. So last days, the previous prior days, we were looking at multiple linear regression, as a, we looked at this tool because it's a starting place for a modeling tool in QSAR, and it's a commonly used tool. I'm going to check just a minute to show the PDF, I hope. Regression book, statistical, no, not that. Okay. We'll go through some of this this PDF that I'm trying to show. We'll talk about it a little bit more, but I wanted to come down to a chart somewhere. It is here. Methods, conclusion, okay. So this chart we're now looking at a chart that is showing, this is from one of the, I believe it's one of the references. If it's not given in the reference email that I sent before, I will refer, we will get that back out in another email, although this is a proprietary book, textbook. So I don't know if you can find this to download, but I found it. In this first chapter of this book, which is titled Statistical Modeling of Molecular Descriptors in QSAR, QSPR. So there's a lot of, just on that note, the QSPR and alternate acronyms, letters are, I've run across a number of different things, but the general field of QSAR, QSAR characterizes a specific thing, quantitative structure activity relationships, whereas QSPR is quantitative structure, it's like bioactivity, but the P. Properties relationships and qualitative structural relationships, all kinds of different acronyms. Don't worry about that. Some people like to use different things. Some people are fine with the regular terminology. Okay, this book on the first chapter has, let's see, I'm on page number 25. Table 1.1 says, number of published studies in PubMed and Scopus with different algorithms as keywords. So this is not a fancy study of this, but it's a quick look by keyword at successful studies in QSAR to try and see what methodology is being used. And I discussed this the first day or two of seminar as well, that the overwhelming usage is what's the years, this is like 2005 to 2010 or something like that. It's not very, very recent, but it's not out of date. And we have among 1,000 or so studies being referred to. The majority refer to in the keywords partial least squares as a data analysis methodology as the number one item, depending on which, and the number two or the number one. The top two, similar, very similarly ranked. Top two tools is multiple linear regression and partial least squares, which is a variant of multiple linear regression. As the tools that are overwhelmingly more used, followed by support vector machines, which is a vector space cutting approach, partitioning kind of approach, which I imagine the number is relatively large for support vector machines because they were kind of popular right at that time, the 2005-ish time frame. I don't see that much usage of support vector machine now. Support vector machine, it's not a machine, it's a computer that you program. It's the algorithm or the methodology is termed support vector machine. There's no machine. And then some linear discriminant analysis, which is a little bit, somewhat a multivariate tool, a little bit similar to partial least squares, and then some newer or more slightly fancier sounding K nearest neighbor algorithms at 38 or ranking number 5. And then we go 6 and 7 is decision tree. I don't know why they separate decision tree from forest of decision trees, but that's fine, whatever. If they combined it, the ranking would change. And then there's very little usage. Gaussian process, I'm not sure what they're referring to. And finally, logistic regression, which is surprising that is not used more, but because it's seems like a well-suited tool for determining categories. But I will try and talk through some of the concepts or the ideas of some of these tools, because the only thing we've really looked at is linear regression, and that we looked at very quickly and briefly. But okay, I'm going to write down some more. So I'm going to go back over to Air Server, and I'm going to go to View Full Screen, and hopefully I did that correctly. So we talked about multiple linear regression and this is really the only modeling tool that we talked about really at all. And we talked about it just a very little bit. We saw in that PDF, oh, I need to get that open in front of me here. Okay, there, it's on my other computer. Helps having 3 computers in front of me. So this is multiple linear regression. Is one popular, one of the common tools, methods, whatever. These are the computational, the mechanical kind of things that so I say tools or methods or algorithms. The computational approach, the analysis approach. One of several common tools, and the most introductory level tool. So that's ranked number 1. So then number 2 ranked tool is partial least squares. This is what I called last time. Can I do this? I called this Iteratively reweighted regression, which is what I've iteratively reweighted partial least squares. It's really the iteratively reweighting that is the characteristic process or algorithmic aspect of this approach. And then I might look to, I need the guidance document here, just a second. Nope, not that. Give me a second here. I'm looking for my guidance document, the one that's intro topics QSAR. Because their topics list, while appropriate to look at and nice, is not the newest thing, and it's not precisely what we see going on. So the Organization for Economic and Community Development, is that what it is? OECD. Oh no, Organización de Cooperación y de Development. I can't speak French anymore. Development of Economies. Which, by the way, I note that the guidance document that I was trying to target in working through in designing the seminar topics, I followed this because it is so widely endorsed, although it's from year 2007. You know, it's this international program. I mean, every international organization is saying, yes, this is an appropriate guidance approach. And their list of tools is what we looked at. I wrote it down several days ago. Univariate regression, multiple linear regression, principal component analysis, partial least squares, artificial neural networks, fuzzy clustering regression and regression, nearest neighbor clustering, genetic algorithms, and they also discuss generally classification models, where neural networks being among them, and a huge number of other topics are in this guidance document. It's very valuable. I especially like their earlier chapters, which are on the domain. Maybe we will talk about that. Model QSAR, model concepts, meaning modeling generally, not without worrying about which tool. There are a few concepts that I'd like to mention if I have time. Let me make it, which are discussed in the guidance document, primarily in chapters 1 and 2, but also going on in chapter 4. So partial least squares I would like to describe conceptually, and then the other tools are a little bit harder to neural networks is a fascinating tool. It's a little bit more difficult to discuss to give an idea of how it works, but I will try and talk about that and some of the geometry-based or metric system based tools. It is frustrating to me because this is the point at which this class could get very interesting and fun, actually using some of these nice, fun, fancy tools to go and do some, and really get into the interesting stuff. And it is exactly when we're ending. This is why I would suggest, if you are interested, please contact me, and I'm very willing to entertain some more hours of discussion on the QSAR modeling topic, because I find it kind of fascinating. So I want to talk about, to put off, let's see, I'm getting confused here, disorganized. Methods. What happened? Methods is a specific thing. That's the multiple linear regression, partial least squares, KNN, ANN, etc. So I want to hit that some, but I will first grab partial least squares and give a brief discussion, maybe not how the algorithm really works, but what the idea tends to, why people are using partial least squares, and some of the issues with it. And then, so going on, that'll be first. Partial least squares. And then second, I want to talk about modeling concepts with domain, training set, train/eval, just some of these basic concept, data, endpoint, which are mentioned and are important aspects that come up in the guidance document for validating these things. Okay. So, partial least squares. This is along with multiple linear regression, the two are overwhelmingly more used than fancier tools. So, partial least squares is a modeling tool, much like multiple least squares regression. It's very much like a multiple regression model. In fact, it starts as a multiple regression model and then acknowledges the fact that there is systematic structural problems with multicollinearity or correlated explanatory variable factors with multiple, where you have many X factors many are correlated, or otherwise functionally connected. So this can be, this is because they're molecular descriptors, and there's a lot of ways of describing things, and you might have various factors, so descriptors, or factors, descriptors. Descriptors x1, x2, xp, that some set of them describes, I don't know, a property. I have to pretend to know some chemistry here to give some example. I hope that my example isn't absurd. I don't really know. So maybe we have a set of X descriptors that are collinear. They're connected function, or connected by a functional relationship closely. And this might be something like measures of, I'll call it volatility. So chemicals, various chemicals that we might study might have, there might be various known in the data, or there's libraries of data for chemicals, but you might have measures of volatility, which would be things like vapor pressure at given STP, boil/freeze information, some descriptor information that relates to, I don't know, a rate of evaporation, which might be in a sense well, might be a related quantity, and maybe along with volatility might be something, some measures that are sort of related with degree of flammability. Dangerous, like ignition point, ignition temperature, or combustibility, you know, oxygen content in the atmosphere that's necessary for combustion. So you could have these measures, molecular descriptors, or X factors that we want to model, that we want to use in our model for some Y value. And we might have a bank of data, or have used some computer software to generate data, which has similar, where you have multiple things that are characterizing much of the same basic information. So if and again, this is a false, contrived example. I don't know if this is really exactly right. But if you had, vaguely speaking, measures of volatility, and you have a number of different physical properties that are associated with the different molecules or the different chemicals that are being modeled, and they are all to some extent saying the same thing of characterizing the degree of how volatile the chemical is, and are different ways of saying that. So things that tend to have a lower boiling point or a higher vapor pressure or higher rate of evaporation or sublimation, or tend to have a high, low flash point, highly flammable, explosive characteristics. Those are things that at least my experience, I would associate with being a more volatile chemical. And so if you have this information, multiple X factors, which are in your model, and they are describing, for example, volatility, and there would be then another set of X factors describing other characteristics of chemicals or molecules, sometimes many, many, many thousands of characteristics, where many of the characteristics are functionally related. They are similar in their behavior. If a chemical is high in one account, on one point, it'll be high or low with a functional relationship in another point. That is the situation. In such a situation, you would have multicollinearity in factors or groups of factors by group. So we have, X1, X2, X5, which are all perhaps volatility measures. And so if you have things like this, where they're all basically measuring the same general information, and so you put in X1 in the model, and then an additional term going into the model doesn't provide much additional information. And in fact, they are within a group of similar measures, they're all behaving in the same way. That is the multicollinearity problem that comes up apparently very often in the QSAR modeling. I say that because of the wide usage of partial least squares. Partial least squares, iteratively reweighted partial least squares, is one approach to fixing the multicollinearity problem without thinking. It's a I don't have time to get into exactly what the issues are and what the problem is with multicollinearity. But what happens is you have standard errors of parameter estimates that tend to just, explode, where you have two things. If X1 and X2 are collinear, if they're related, provide the same information to the model. It doesn't matter which one you have in, but if you have both X1 and X2 in the model, then you're going to have one that's a reasonable thing and one that's crazy. This is often what happens when you have multicollinearity problems in a model, is within the collinear terms, one of them is acting somewhat reasonably and the other behaves somewhat irrationally, large fluctuations, very large standard error. And it's really because because there's no additional information. It's not a useful factor with the first one in the model already. Now, normally statisticians take a careful kind of approach to sorting out multicollinearity issues, but there is a kind of, because you can't have them both there. So there's an approach which is less analysis, less work for the analyst, less work for the analyst, less understanding, more computation, and analogous to reduction of dimension tools. So to address the multicollinearity problem with a related set of measures, there are approaches which would keep a standard multiple regression model and simply start removing X factors from the model until you reduce it to a set of just the X factors which are independent in their behavior across the different observations. So that's a high workload tool. There's also an approach of looking at looking at it in the sense of a principal component analysis, which is, boy, this is hard to, well, you really need the linear algebra terminology to imagine the X factors and the Y factor, everything as a large, high dimension, very high dimension vector space, where the data is populating some, does not populate the whole multi-dimensional space in every, across every domain. There are places where there are similarities in the information that is contained in variables, which essentially means that the vector space is not full rank in a sense. It's just not full rank with the number of dimensions in the explanatory factors, and so you have this this situation. I mean, that's the first thing that you have in multicollinearity problems, is if you have a matrix that won't invert, which if you've done linear algebra, you know, of course, if you try and do the solution to the equations with a less than full rank matrix, you're not going to be able to invert it, and the whole thing, that you can't do any of the computations. Because of the error terms, you often can invert the matrix, but you need to stop that technical discussion. If certain X factors, if a set of X factors like X1, X2, X3 are largely giving the same information, but it is, there are dimensionality reduction tools that look at, for example, linear combinations of factors which reduce 3 dimensions down to 1 or 2, whatever. Dimensionality reduction tools are very nice and handy. They are sensitive to distributional issues with data. There's a lot of practical operational issues that require experience and knowledge and lots of time to explore. How do you separate these 3 measures of volatility into just one measure? You can get rid of terms, but most likely what you want is a new X prime 1, which is sum of a weighting factor times X of I from I equals 1 to whatever, but 3 in this case, where the 3, a new factor might be defined in terms of a weighted, it's a linear combination, defining a linear combination of other factors of x1, x2, x3, and then we're left with x1 prime in the model. So we have a single factor, the prime one, which combines x1, x2, and x3, combines the information, combines that data with some, there are many different ways, but the simplest thing is with a linear combination of the 3 with some specific weighting factors. The sum of the W's is 100%. So you kind of, it's like a weighted average of certain factors and reduce down. So that reduces from 3 to 1 dimension in this aspect of the model. There may be hundreds of X factors, but this weighting, this sort of readjustment can be done with multivariate tools, and it can also be done in this partial least squares, or this iteratively reweighted PLS, partial least squares. And that's and this is a computationally intensive, but takes care of it without thinking. Low thought, high on computer. And it basically applies an algorithm to reweight, to apply weighting factors to all of the X factors in the model, where software allows with controls. You can give it parameters to control the way it does the initial weighting, and then the iteratively reweighting the factors until it achieves some convergence criteria of collapsing collapsing many X factors to a few, meaning lesser, to fewer factors, which are, I'll call it X prime factors, X1 prime, X2 prime. There are fewer of them, and each one is some weighted average or linear combination of the original X factors, and it represents a lower dimension, fewer dimensions, fewer factors is fewer dimensions, but the dimensions that are represented are more completely filled rather than being so you have something much closer to a full rank matrix and you can think of it as collapsing onto the hyperspace that is actually populated by the data. If you think of the high dimensionality vector space of factors, and whatever the hyperspace is that's actually represented in the data is some, cuts through. It's crosses of hyperplanes that are all at different angles but the space, the whole space is very sparsely filled. Much of the data lies on these hyperplanes, and it just is basically iteratively trying to search through some reweighting factors to those. You can think of the weighting factors as being the vector or the matrix transformations, which would map a vector down to the hyperplane and have it straightened out, so it's kind of like a new basis. And but you don't really know what the hell it's doing when it does this. It just does it, and it's a result-oriented algorithm. So people do this result-oriented, which is weak on explaining why the weighting works the way it does. Why does it do what it why does it work the way it's working? There's not much of that. It's a little bit in a sense of a black box type approach. Not completely, but you still have factors and can control these things. The problem that you have that then comes back in, problems. First problem is computational. This is like doing the multiple linear regression, but doing it thousands of times for each model. Instead of running a model one time and getting the estimates and changing something and running it again, every time it runs, it has to do the iterative reweighting, and so it's going through thousands and thousands of times to do this. If you have a large model, that could be very slow. I don't see in the literature I've seen or in the books, I don't see evidence of this being a major issue. Because the things that they do, that chemists do in QSAR modeling, everything I see looks like these tiny little data sets. I mean, the largest thing you see referred to is something like 100,000 chemicals in a database, and really 100,000 of anything. I mean, that's just nothing from the perspective of large data work with all the time. Second problem is sensitivity. I don't know if the guidance document discusses this in particular, but it's something that I certainly recognize as a potential problem with partial least squares, is that the way the weighting factors get sorted out as it goes through the iterative reweighting algorithm, the nature of the weighting that it comes up with to solve the model in the end is important, because if it with a different weighting, the solution will be all different. But it's the nature of the weighting is important, and the nature of the weighting is very sensitive to outliers or extreme values, extreme X values. This is a huge concern with any kind of data involving humans, because anytime you have anything that involves people, you always have crazy extreme values that are often real but very difficult to explain and make sense of. With physical and engineering, chemistry kind of data, it's less likely to have extreme values of chemical information, descriptors of molecular descriptors within a well-chosen class. So this is maybe, well, it's still a problem with this, with partial least squares. Third is lack of lack of understanding or lack of interpretation, lack of good interpretation. Because you have these factors that have however many p different weights. Each different factor has all the different weights. It's very difficult to sort out what exactly that a specific factor is trying to tell you. And that's where you do then, perhaps after you do this, maybe you go on to a principal component analysis, a factor analysis to chop this stuff up and see where things are. But anyway, it gets the job done. It gets rid of the multicollinearity, because with each weighting iteration, it's pumping more. It's combining more things through the weights down into fewer adjusted factors, linear combinations. That is a smaller set, but picks up the right mix of information from the larger set of collinear variables, and then does this sort of degeneration of the. There. It's a nice idea. It's a nice tool, widely used. With the computationally intensive, I don't know. I've never run these in QSAR context. I don't know how much of an issue it is. The sensitivity to extreme values, I see increasingly references in the QSAR literature and books about applying a variant. So partial least squares, variant. I don't know what they call this, but it's using quantile, like M or L statistics, where instead of it fixes the problem that can come up in the weighting, in the iterative re-weighting, in the deciding about the weights. It can address the problem of the sensitivity to extreme values by considering additionally or solely the percentiles of data across the distribution as opposed to the absolute scale value, and that limits places a limitation on aspects of precision and measure and metric characteristics of information. It limits that, so you lose some information, but you also simultaneously are limiting to a fixed, defined domain with a metric, and nothing is extreme. And this is used, I can't remember the name of it, but it's used increasingly in the QSAR literature. And again, it's a good, this variant provides nice, provides a nice solution with a lot of computation and little understanding of what it's doing. Okay. That is my my non-technical description of partial least squares. And I'm going back here. I wish I could go faster to where I made my little note on, oh Lord, on modeling QSAR model concepts. Okay. I'll try and, so after, I wanted to make sure I just made some mention of partial least squares because it is a common, very common tool. And also becoming common is the sort of less metric, ordinal type approaches to partial least squares which address the sensitivity to extreme values. So then now is, instead of discussing the many other tools that are different from regression, some of the alternate tools are similar to regression, but some are very, very much different. Classifications and groupings and clustering tools. I'm going to first talk, before I mention that, I want to talk first about some model concepts, and that will be best come after our break. We'll break in just a few minutes as it approaches 5:30. I'm going to just make a few notes to come back to after the break. So modeling concepts. I refer to reference is the OECD guidance. Which is in the email of references which was sent out several weeks earlier. And I'm talking about the topics in the table of contents. Well, the guidance document is specifically a guidance on validation of models. So it is there is an overemphasis on validation and an underemphasis on process of modeling, but rather the validation that comes after it. So understand that, but so concepts of data, your analysis is only as good as the data. There is a lot of importance in having the right data and having the data be what you think it is. Data, endpoint, clearly defined objective in the modeling. These are discussed in chapter 2, a defined endpoint, and page 22, page 24, importance of quality of measured endpoint data. Yeah. Statistical error is far less likely to occur than human error and lousy data error in terms of errors that you see in studies. Data endpoint information, domain, or the chemistry context. This is making sure that the domain or the universe, that it makes sense. Statistics can't answer that question. Statistics can't determine yes or no what is the universe of chemicals or the class of chemicals that makes sense to use. That's what a chemist has to do, and then conclusions can be made within that domain. That comes up in, well, probably in the validation, chapter 1, and applicability of domain applicability, model applicability, non-extrapolation. And then I think I have to talk about training. I would also talk about validation, but there's no way I have time for any of that. Okay, so we do break 15 minutes, come back at 5:45.